All right, we start. Joe, how does this work? We on Berkeley time? I actually don't know how the seminar works.
You're doing a great job. Then we introduce the speaker.
Wait, hold on a second. This is the Rise seminar. Happens every Friday at 11. Okay. Today, we're honored to have Chris Ray up here from Stanford. How should I introduce Chris? Chris has all sorts of accolades. Hopefully everybody knows him. There's a nice crowded room. Seems like he doesn't need an introduction. Other than the fact that Chris and I met each other at Wisconsin, mostly because we were season ticket holders for the Badgers. And so I think probably the greatest moment we shared together. We wrote some papers together too.
Those were not good.
But when we saw Wisconsin play Ohio State, and there was this really loud guy from Ohio State sitting next to us. Mostly this was Joe, by the way. He was also from Wisconsin. There was this guy from Ohio State sitting next to us, talking a lot of smack before the game, very confident that they were going to win, and said that if I don't exactly remember how this happened, but he said, if you guys even score against us, I'll buy you hot dogs. And then Wisconsin returned the opening kickoff, and then he shut up.
Yeah, he actually had to move sections. That was what was like. But he was a class act. He bought the hot dogs not just for us, but also for the front row of all the kids who were in front of us. He was a class act. We should add that to the story.
I feel like it's a metaphor for something.
Yeah, there's a deeper meaning.
There's a deeper meaning about the work Chris and I have done since. We'll figure that out through this talk, where Chris is going to talk about a lot of the stuff he's been doing at Stanford. Actually, a lot of stuff that he started doing at Wisconsin, realizing how kind of the most important part of machine learning wasn't algorithms, but the training data itself. So I think that's what we're going to talk about today.
Awesome, yeah. So thanks so much, Ben. So the thing that I've realized when you start to build kind of machine learning products and start to build them and send them out into the world is, you get this kind of advice that says, like, if you want to build a really good machine learning system, what you need to do is build a really high quality data set, training set, to be able to build that algorithm. And this, to me, always felt a little bit like the title of my talk. Like, if you want to be rich, get a lot of money. Like, it's true, but it's not really operationally useful. Like, what does that tell you to do to go collect a good training set? So one of the things we've been doing for the last couple of years is trying to understand, are there sort of systems and theoretical tools that allow us to understand what people are doing when they construct these training sets? What's a good or a bad thing? And can we build both a statistical theory of how we do it and maybe offer some interesting software abstractions? And so this has been going for a couple of years and caught on to an extent that honestly stunned me. Like, the number of products that probably you interact with today that use it is pretty ridiculous. So I'll talk about that in a second. So backing up a little bit, at a high level, an ML application, you can kind of think about it as having three kind of parts. There's the model, there's the data, and there's the underlying hardware. And I think one of the things that we've been blessed with from sort of the cloud service providers and the rest is that you can, by and large, go out and get amazing hardware in kind of elastic quantities whenever you want it. The thing that I think is less well understood is that, especially for folks in industry or who are doing scientific collaborations, actually state-of-the-art models are available, right? Great places like Hugging Face, you can pip install the latest and greatest models, like pip install the transformer models that they just came out with today and install them directly in TensorFlow. So in a way, like, state-of-the-art models and hardware are really available, and they're not the bottleneck, even though we spend a lot of time and effort on improving both of them. The thing that does seem to be the bottleneck in every application that I've ever seen is the training data, okay? And that's kind of natural if you think about it. That training data is not just some data that you throw or feed into the system. It is, in a real sense, the specification of what you're trying to actually do. Like, it's your code, it's your program. That's the way you teach the system what you want to do. And so cleaning that up and understanding it, that seems like it should occupy kind of a first-class role in machine learning. Now, when I teach machine learning, we get up, we had supervised learning on Wednesday. Well, what is the first thing you say in that lecture? You say, well, there are X and Y pairs. Well, where did those X and Y pairs come from? Well, God herself. They just fell down from the sky. We have these X and Y pairs, and then and only then do we start doing machine learning. Now, that is okay for 229, but doesn't match the felt experience of pretty much anyone who's ever built an industrial-sized kind of product, right? This is my most expensive picture in the talk, by the way. This is a $50 picture of a sewer that I bought, that I'm very proud of. So training data actually usually comes not by God or from God herself, but comes through a process, right? People augment their data, they grab old training sets, they start to denoise them in some ways, and they throw them in, and they spend a bunch of time there. And so all that I started asking a couple years ago is, can we provide some mathematical and kind of statistical tools to open up what's going on upstream of that? And as I'll argue, yes, there's a bunch of statistical stuff that we can do. And then also, can we build some software support to be able to help this out, what people were actually doing, to help them hopefully build these high-quality systems a little bit faster, more robust, and all the things that you would like to get from these kind of pipelines. Now here, I'm going to go one step further. That was not what we were thinking when we started it, but actually, we started to realize that actually supervision is in a real sense where all the action is. And I'll argue that actually in scientific applications and even in benchmark applications, model differences are largely overrated, and the quality and quantity of supervision is largely underrated in terms of success. And that has a pretty big impact about where we should spend our time, kind of as either statisticians, machine learning, or systems people, okay? Now, when I say that, I'm serious. Like, I actually try to build real applications with real folks and understand what's going on. And one of the things that we built was this automated chest triage thing, which is an interesting thing that I'll share with you. You can notice all the physicians, they have ties on for whatever reason. Physicians love ties. So we decided we were going to build a data set for clinical triage, okay? Now, so what's the problem? So you've probably heard variants of this in Wall Street Journal and other places. There are a bunch of x-rays that are taken, but unfortunately, people don't look at them, okay? So they don't have either the expertise to look at them, so your GP looks at, just takes the image, but doesn't actually have time to look at it, or they don't look at it while you're still there. And so, this has been written about kind of endlessly. Wouldn't it be great if machine learning could take a look at some of those images and just triage? Hey, there's something you missed. You missed some pneumonia, you missed this particular condition, whatever it is, okay? So this is something where genuinely I would love if machine learning could actually help us. And so the question is deep learning actually the answer to these things? These modern methods, is this going to really help us be able to build these kind of triaging systems? And it turned out that that's kind of a superficial question, but answering it isn't very easy. And the reason it wasn't easy is at least a year and a half ago, there was no benchmark data set. Actually, last week, there was a big release from the RSNA, which was great, the radiology folks. Actually, some of the guys in ties released it. The effective data quality is actually totally unclear on various different benchmarks. So one question I will plant, if you don't have questions in the Q&A, is why don't you trust machine learning people to do medical applications? And I have a 3-slide rant about that. The last thing is there was no assessment of existing algorithms. We had been just as guilty about this as other folks. We had Nature, comms papers, and other things that were saying, hey, look, here's one baseline that people are using. Here's how we improve it for some particular triaging or cancer task. But it didn't assess how that really impacted the clinical side of the world. And it didn't really have feedback from the clinical community, hence the need for the people in ties, okay? So Jared spent a year trying to answer this. He created a huge data set of clinical labels. He evaluated the effective label quality. He had board-certified folks actually go in and clean up the labels that were in some of the sets that were collected, make sure that we understood and actually had crisp definitions of what we could classify and, importantly, what we couldn't classify. And he made sure that he published it in a clinical journal, who then went back and said, hey, here's what you got right. Here are the places we think are interesting for further study. Now, for our talk, what's important is that after you do all that work, here's DenseNet. DenseNets are awesome. I love DenseNets, right? Killian stuff is awesome. ResNet's also really good, but not that much better than KSVM with bag of features. And this is not like, alien technology. This is old. And so you're talking about a difference in model that's 2 to 3 points on these kind of clinical applications. And that's kind of getting back to my point that maybe the models, the newer models, are not where the accuracy is. So I'm going to come back to this application in particular in a follow-on paper that was just recently accepted, that label quality and quality actually make a whole lot more difference than model quality, model choice for these kinds of applications. You should always use the latest and greatest models. Model research is great. We do it too. But this is something that seems really understudied. Now, when I talk about this with machine learning folks, they say, oh, maybe those are just some medical jokers. those medical jokers, we wouldn't do that on our benchmarks. Well, no. Actually, data augmentation is actually responsible for a huge fraction of the gains inside CFAR. There are a couple of recent papers where folks, kind of handicapped one model and gave it access to data augmentation, and then the other model, didn't have access to it, and the differences were pretty well explainable by that. So if you're a very, niche follower of this area, you know almost exactly which famous paper I'm talking about. But the point is even if you survey across the top models, if you take out the data augmentation component, all of a sudden their performance radically drops. And the same thing is true in NLP kinds of applications. It's also true to pushing the state of the art, right? So state of the art results on things like ImageNet, actually new augmentation policies are a great thing. Alex and Henry had this beautiful thing where they just had this idea, said instead of augmenting in the pixel space, lift up, try and know some little bits of transformations and learn good sequence of transformations. And Google spent a huge amount of money and beat the state of the art. Awesome. And it's a really cool paper, the idea of trying to figure out how to learn these augmentation policies. Facebook's did something similar. Okay? So my point is that I've argued that training data, in a real sense, augmentation, labeling, and other things, are really a bottleneck. But probably you're still stuck in the model of like, well, what the hell can we do about this? How can we actually build either a statistical theory or a systems theory that's going to do anything about this problem? So I'm going to first argue that training data actually has some things that are pretty nasty about it if it's done in the current kind of way. Then I'm going to argue that at least sometimes we can improve those things. Okay? So I'm going to argue that it's slow, expensive, and static, and that we can do a little bit better than this. Okay? So what do I mean by this? Let me unpack it. So manual labels are really slow. The reason they're slow is basically the time it takes you to produce your last label after kind of an initial startup is basically the same as it takes you to produce your first label. Okay? They're expensive. We're going to look at applications, I'll show you one, where the background incidence of the phenomenon you're after is like 1 out of every 200 videos actually has the defect that we were looking for with these radiologists. That means they're going to have to look at a huge number of hours of video to be able to find the abnormality actually that they were after in this case. And those radiologists don't come cheap. Those ties aren't going to pay for themselves. The last bit is that these things are static. So this is something that anyone who builds products knows and has struggled with. You get everybody around the table, you say, here's what my machine learning model is going to produce, here's my specification, my schema to you, and then you take it from there. Then the application folks who are downstream say, you know what, you told me if that was positive or negative, but I also needed neutral. And now I have to go back and revise all of my training data, and that costs just as much as effectively collecting it from scratch. Okay? So we're going to look at one paradigm. There are many to address this, but we're going to look at one that I'll talk about that we're excited about, which are these programmatic labels, which I'll define in a minute. They're going to be much faster. They're going to run at the speed of programs, so you're going to have to encode some little bit of knowledge. They're going to be cheaper because they're going to run at the speed of machines rather than at the speed of humans. And they're going to be more dynamic because we're going to try and change training data from this very manual coding up zeros and ones to giving you like the structure of like what looks like an assembler, like an assembly language for dealing with these kinds of supervision problems. Now the trade-off is going to be that the labels we produce in this way are going to be much noisier. Okay, potentially. And so the theory that we've developed is how do we deal with those bits of noise, and how do we deal with the correlation among all the sources we're going to produce? And that's going to occupy a central theory of like the math that we're going to do to try and make this whole bottom thing actually come into reality. Okay? So let's see how that works. So in this talk, I'm going to tell you a little bit about how we generate this one bit for labeling, because it's the one that's kind of well developed and caught on first. You can do the same exact things for augmentations. It's on the website. Slicing, all kinds of other tricks that are there. We're going to talk about this core technical problem so we can at least have a little bit of math. I think that's something we should have, which is this approach to learn kind of quality and correlations of sources without resorting to training data, right? We're not just going to punt the thing to label more data. And then we want to talk about the different end models where this is actually used. Originally, because of like the idiosyncrasies of my lab, we got a lot of traction in kind of like things that look like ads or text, just because of the folks that were around, but it's now on videos and images, and I'll kind of flash through a bunch of those because I know folks are applying it in those new directions. Okay? All right, so what is this programmatic labeling? Well, I would say if you're a machine learning person or a person who's built products for machine learning, you already know these techniques, these programmatic techniques, you just know them under different names. Marty Hurst did pattern matching in the 90s. It was awesome. Every NLP person worth their salt has used them in some kind of application. Snowball is another one that was great. Distant supervision from Jurafsky and Mintz. You have a knowledge base and you can supervise data with it. The point is there are many of these that you've seen where people are acquiring lower quality data, and that's the way they're thinking about it. Okay, that's like their trick. And in fact, if you look at NLP papers, you'll often see entire papers dedicated to, here's how this technique works, and I got it to work on this particular domain, which is super exciting work. Okay? The observation that we made was that these weak supervision techniques were usually applied in ad hoc ways. So people had their own way of incorporating this information, and they weren't able to combine them effectively. And so you would go to one team in industry, and they would have, they say, you know, we're a pattern matching shop. You go to another team in industry and say, oh, we do everything by data augmentation. But clearly, these things should be combined. And we need some way of just talking about them in a principled way. So that's what this thing Snorkel is. Okay? Snorkel, what it decided to do was take all those different kinds of weak supervision, as many as we could, get a very general abstraction, which are these things that we call labeling functions. And the idea was to capture all the things that people were doing everywhere. And we were just going to, the thing that we realized we could do enough with was to say, we're going to capture the source, the style of transformation that you have. And you'll see how that works concretely in a second. And then what we're going to do is we're going to do that, we're going to then take the training data that we have, and we're going to estimate for every point what is the probability that's in every different class. So instead of having a single class, we're going to get you kind of a smooth label over them. And then you're going to train whatever deep model you want underneath the covers. Okay? This paradigm we've relaxed in several ways, but this is the basic setup. Okay? So let's look at an example so you can see what these concepts look like. Okay? So let's say we want to do like the classical NER task. We want to label, you know, doctors and hospitals and other things in text. You can do hierarchies of these things, person and organization, doctor and hospital. For weird reasons, I'm going to look at person and hospital together. We don't have to look at multitask stuff, although for various reasons, Snorkel is natively multitask. So the idea is, how will we come up with labels for these things? Well, there's a couple of ways. We could have an existing classifier. That existing classifier is not perfect. Maybe it was trained on a different set of data, and it says person on here. We could write another little Python function. These are these labeling functions I was talking about, which also has some refinements on top of the off-the-shelf classifier, and also votes person. And maybe we also want to encode, you know, Jarofsky and Mintz heuristic. We can just look things up in a database of hospital names. And the point is these things don't agree with each other. They conflict with one another. And they're really obviously correlated in some way. So we have to take care of the fact that they're inaccurate, and we have to take care of the fact that they're correlated to try and make progress. Now, we could just label a bunch of data and get all their accuracies out. But that seems to kind of defeat the purpose. So what we're going to try and do is estimate all of this goodness without looking at any training data whatsoever. Okay? So this is how the pipeline runs. Users write this stuff, these labeling functions. Then what's going to happen is we're going to estimate the parameters of this underlying graphical model. We're going to use that graphical model to estimate the source accuracies and their correlations. Then we're going to do forward inference to spit out some probabilistic training data. Then we're going to pick our favorite deep model and put it in. And if you're an expert, we're basically just lifting off the heads, the final losses, and changing them with labels. You can do smarter things, but that works. Okay? The important points are that this probabilistic stuff is carrying more information about the source accuracies. It's boiling it down in a way the discriminative model can use. And you don't use any hand-labeled data to estimate those sources. Okay? So in the training loop of a lot of systems, and I'll talk at the end about production systems and why this has been so significant, in the training loop of the production system, you may have no hand-labeled data. You do use hand-labeled data to verify the output. That is a sane thing to do, to randomly sample and make sure you're not diluting yourself in your test sets. But in your training and even your dev set, you may not have any hand-labeled data whatsoever. And products that probably you've used are built this way. So why the hell would you do this? Why does this even work, right? We have one model and we're feeding it to another model. What the hell's going on? So one thing that happens is that both as a function of how people write these things and for a function of what happens when you move them across classes, when people write these rules, they tend to write very precise rules. They don't have a high recall, but they have a high precision. No matter how much you try and yell at them to write lower precision rules, they just won't do it. And so they'll write these rules, and then what we hope is that we'll actually be able to boost their coverage and their recall by relaxing them systematically. If we could write the rule precisely with 100% accuracy, don't use machine learning. But this is usual case where you want to use machine learning, where you can write it kind of, and then you need the machine learning to kind of optimally relax it. And so this is something that goes on. So what's an example of this? You have some keyword-based labeling function, you know, treats, causes, induces, prevents. Say you're looking for diseases kind of words. And then the model relaxes it to linguistic phrases. Those are, you know, you've boiled the ocean to get your BERT. BERT should be able to do this kind of clustering for you automatically. Okay. A second reason that these things caught on is that a lot of applications have this phenomenon where they have lots of unlabeled data, right? But they don't, for whatever reason, have enough labeled data. And it turns out that as more unlabeled data comes in, if your supervision is represented as code, you can just continue to pipe it through the functions and generate more weak labels. You may wonder, is there any value to doing that? Do you saturate this? And at least at some very large scales, the answer seems to be sometimes, but not really, not always. In fact, this is just one schematic graph of an actual experiment where as you increase the data points on the x-axis, your accuracy keeps increasing. Okay? And this is a way that, for example, as I'll talk about, we ended up getting higher results on superglue and glue was basically this phenomenon. Okay? The last reason is somewhat subtle that you may want to do this. So the idea here is we want to do that image classification task. Okay? This is one way to do it. But labeling those images is really painful. Maybe 1 out of every 200 of them actually has the image, and putting them in front of radiologists, we're only going to be able to collect hundreds of labels for them when we need thousands to train our model. But someone has actually gone through these at some later date and actually written a report of, this person had this condition. If we can extract the information from this piece of text and use it to transfer as the label, that would be awesome. And the point is that this thing is what we call servable, that is available at test time. We have a classifier just for the image that doesn't rely on the report, which is not servable. When you walk into the doctor's office and take the radiograph, that doesn't generate the report at that moment, right? Like the report is generated later. It would be worthless if we relied on this information. So this difference in cross-knowledge transfer has been really interesting, and I won't bore the folks in the room with this too much, but this is how we've been starting to write all these papers about kind of multitask theory and transfer learning theory based on this kind of split. And this has been a really kind of fruitful way to view the universe. More pragmatically, hours of weak supervision on this, actually a postdoc in an afternoon, and I'll show you these numbers later, actually managed to meet person years of radiologist time. And there's a huge data collection effort. This is in a Nature paper now. And there was even another Nature paper this week, an NPJ digital medicine paper about doing this with the VA for a data collection effort that went on for multiple years, where basically they were able to go in and write these kind of programmatic rules and match, and in some cases exceed the quality of what they had done in the hand labeling effort. Okay. So this is the slow, expensive, and static is what we talked about. Programmatic labels have these advantages, but we have to deal with noise. Now at this point in the talk, given my Raiders hat and dinosaur and general demeanor, you probably think, well, this is some joker. No one's going to use this crap. And I would think the same thing too. And actually, I did. When my students came to me and said, like, is this going to be useful? I said, that's the wrong question to ask. Like, we're not in the game of building widgets here. I don't care if anyone uses it. It's interesting. And that didn't work. So then they built software. So they built software, and one thing they did is they put this Snorkel thing up. It's now used in hundreds of places. So I was at a Google conference, and they told me a bunch of places internally where it's used in Google, and it's kind of staggering the amount of places it's used. Publicly used in places like Apple and a bunch of other folks here. Those big companies. It's used by small neuroscience startups. It's used by one graduate student at a lab bench inside some cancer place in UPenn who sends us a lot of email. Like, there's a lot of, I shouldn't say that, this is recorded. Oh shit. Anyway, so it's used in a bunch of places, and it's used on images, it's used in self-driving cars, it's used in a bunch of random places that we didn't anticipate. So what does that mean? Did we do a great job on the software? Well, I didn't do it, so maybe. But probably it means there's a little bit of a niche here, that this part of the pipeline is very much underserved for some set of applications. Maybe not all, but for some set of applications. Of course, as I mentioned, I didn't do any of the real work. Stephen Bach, who's now at Brown, did a bunch of the work at Google, and he's still interning there. Alex leads Snorkel and is just like a superhuman, so he's awesome. They also decided that they wanted to participate in these benchmarks. I actually didn't like that, but for a brief time, we were the best at glue, and then super glue, and then then all the mighty parameter tuning hordes came out of the woodwork. So we did beat all the BERT stuff, but we don't beat the latest Albert or whatever it was this morning from Google. Yesterday, I guess, Albert was. Anyway, these are the folks who did this. Ines is spectacular. Jared is the one who did all the radiologist stuff. Okay. I won't get too much into this because I want to get into the math. The Google collaboration, we wrote this great paper. Stephen Bach and Alex really led it. But the point is they kind of categorized within the organization what are the sources of supervision that you have to bring to bear, right? So what are the things that are laying around if you're a large web company that you could use? And they had a bunch of different interesting ways that they started to use it, and that was really exciting to learn about. They also had this thing about servable versus non-servable features, which I mentioned in the medical setting, and that seems to be this kind of weird split of like what do you materialize and what do you not avoid materializing. It seems like it deserves more study. Just one thing I wanted to highlight. Okay. So I don't know how deeply I'm going to get into this because I want to give you a rant about a piece of code I did write at the end, but I want to give you a little bit of math. So
Can I stop you?
sure.
I missed something along the way that's going to matter here, I guess.
Sure.
Which is, how do you get the parameters for the graphical model?
We're going to talk about it right now. Awesome. Yeah, so what we're going to look at the math. What we're going to do is say, how do we estimate those parameters without access to training data? Okay. So we have no hand-labeled training data. That's the magic trick. The mathematical framework has been rewritten many times over the last couple of years, and I have to write it up for the last lecture of 229, so hopefully it will get even a little bit better, or undergrads will put my head on a stick. So here's what's going to happen. We have this thing about representing these labeling functions, and now we have this question. How can we do anything at all without having any ground truth labels? What the hell is going on here? How can we estimate the parameters of this model? And is it horribly expensive to do so, even if we could? Those are the two questions that should be on your mind right now. Okay? So how are we going to do this? So we're going to model this as a generative process. The idea is going to be that every function is going to be called on a bunch of different data points. And that function, just for the simple model, has a hidden accuracy. So function 1 is 90% accurate, 2 is 80% accurate, but we don't know or get to see that piece of information. We do get to see how they vote. They all vote on some underlying ground truth. The problem is we don't get to observe why. In the classical supervised case, you would give me examples of why, and then I could just back out what their accuracies are and their correlations. It'd be a simple counting problem. Okay? So how can we do anything? Well, here's the intuition. The intuition is that we can learn for when they vote on the same object, how often they agree and how often they disagree. If, for example, we had one source that was 90% accurate, then it'd be relatively easy to see how often it disagreed with those other pieces that were there, the other two. If on average, they're bigger than 50%, right, like they're not adversarial, they're not all wrong, then we should be able to back out an estimate, and it's a statistical question of how much noise can we tolerate. And so I'll show you the math that allows us to make that more precise, but that's the intuition. You're going to see many, many different votes. You're going to see where they agree and where they disagree. As long as on average they're closer to the truth than not, we should be able to pull something out of that. And the statistical game is how much noise can we tolerate? And that's what the series of K papers are really all about. Okay? All right. So that's the key idea. Aditya.
Is there some assumption of independence across these functions, labeling functions? Because I see an analog here to sort of the crowdsourcing
Sure.
thing where you have independent
Awesome.
workers giving sort of their labels, and then you're using majority vote in some sense.
Awesome question. So we will obviously compare with majority vote and crowdsourcing approaches as we go through here. And just going back to this graphical model, we actually don't make an independence assumption because we're actually tracking the correlations. And so one of the big differences between like the Karger-O paper, since I know you're an expert in this area, and this is that we want to estimate these correlations. And because they're writing functions that are manipulating data, if you don't take care of these correlations, in some applications you go horribly, horribly wrong. Like if you took the same function and just copied it 100 times, that would obviously not give you an improved estimate. So you have to keep track of this information. And that's the key technical difference here. Yeah, and we also have a paper in VLDB that says, hey, sometimes majority vote works really well, and we identify the regimes where majority vote is actually going to outperform doing something that's smarter, and there's a slightly better estimate, this medians estimate, that you can also do. Anyway, but this is the general case. Great question. So how do we do this? So we're going to look at this covariance matrix. Give me one slide to explain why I care about this covariance matrix. The interesting thing here, so on the rows and the columns are the random variables of that graphical model that are over there. Okay. But we can only observe part of it. And the reason is this y we can't observe. We don't get access to y. So we can't observe any of the measurements that also involve y. Y squared we can observe if you imagine that it's minus 1, 1 for the moment. That doesn't actually matter. But this is the part that we can always reliably observe. Okay. Now, why are we looking at this thing? Well, if we could compute these values, it's pretty clear that we could get a function that would allow us to compute the accuracy. If we knew how often, so the dot product of y and lambda were true for lambda I, that would be how often does it agree with the ground truth. Okay? So that's the number we're after. So we'd love to be able to fill in those components. Now it turns out that since Clifford Hammersley, since like 70s, people have known that you shouldn't look at the covariance matrix if you care about graphical structure. You should look at the inverse covariance matrix. And the reason is roughly, and I don't know the politically correct term for moralization now. There's got to be a better term than moralization. That feels wrong to me, but this is what the process is called. But in the statistics literature, this is called moralization. If you moralize the graph, which does some cleanup, then what you find out is that effectively, whenever there's an edge missing in the graph, there's a 0 in that entry in the covariance matrix. Now, for now, to simplify the math, I'm going to assume that you give me this covariance. So you tell me which of these things are an over-approximation of which functions are correlated. In the second part of the talk, if we have time, I can tell you how you can get around that assumption and learn the correlations and what the assumptions are that are there. But for the moment, imagine I know the structure but not the parameters of the correlations. How can I learn this? Well, I need to use one idea. This is just a math trick. I can write that sigma O in terms of, this is the inverse covariance matrix at the O that I've observed, in terms of this thing, which I actually observe. I can just observe that matrix and invert it, okay, just for the moment. And then I get these free parameters that happen to be rank 1, okay? Now, these are just a straightforward function of the accuracies. If you write out the matrix inversion lemma, you'll see what they are. They're just a rational function of the accuracies. But just kind of think about them as the accuracies. There's 0 when an accuracy is 0, or ZI is 0 when its accuracy is 0.5, when it's kind of random noise, and it's 1 if it's perfectly accurate. Okay? All right. So good. So now we have this thing. So now we have a bunch of equations, because we know the graph structure, that look like this. Okay? They have zeros in some places, and we need enough of those zeros. And intuitively, for exact recovery, it's obvious what you need. You need those zeros to form a full rank mask, right? They have to have enough zeros, at least one in every row and column, to be able to recover all the parameters. You can prove that that's true. Question is, what happens when we have noise? Now, this looks a heck of a lot like a low-rank matrix completion problem. I'm sampling some entries. I'm trying to recover some low-rank version of those sampled entries. The problem is that usually assumes that the underlying object you're looking at is near to something that's low rank. But this covariance matrix is full rank. You look like you're screwed at this point. The key idea is that actually it has a particular form. And its particular form is that it's very strongly diagonal plus a rank 1 term that's off the side. And that rank 1 term, if everyone is just complete noise, would be 0. So you would just get back, an identity matrix here. There'd just be, randomly, independently flipping coins. You would not expect to recover anything meaningfully. But intuitively, when that U is big, that means there's a lot of signal that's underneath the covers here. It's close to 1 or it's close to -1. And that's telling you when that norm is big that there's something that's underneath the covers. Okay? So a couple of technical comments. First, we should be really suspicious of any solution that wasn't symmetric. But obviously, there's a symmetry in Z. If I take them and just take Z and minus Z, I get a flip. And that's obvious, because if I don't know what true or false is, the model isn't imbued with special powers, it only sees the votes. So you would really expect that symmetry to be there. And that was that talking around why you have to make an assumption to break this symmetry, like on average, they're not adversarial. Or you could recover the wrong one. We have tighter conditions. When ZIs are 0, that means the accuracy is 0.5. That means you're going to need a ton of samples. Why? Well, if one of those parameters, let's say Z1 is 0, then 2, 3, 4, 5, every measurement gets zeroed out as well, and you would not be able to recover in that situation. So you need enough of these parameters that are bounded away from 0.5 accuracy that you have a hope of recovering them. And that intuition, although it's discrete, it's this 0 multiplication, that will carry over continuously. The last thing is, and this matters to probably no one in the room, is that what you can do is relax the notion of rank that you're using instead of using a classical notion of rank and use an effective rank computation. And this is something that comes out of Verschinen, and Verschinen's notes in 2012 is the source that we use for this stuff. And basically what it says is, as long as this thing is large, this quantity is going to be bounded. And so even though you had something that was low rank, you have something that's low effective rank, then you can use the great stuff that Ben, Emmanuel, and Terry did. And you're kind of like back into the good stuff. Okay? So you're bounded away from pure noise. It's basically all good. Okay? Awesome. It turns out, weirdly enough, that this notion, I probably won't have time to go through it, but this notion also allows us to learn structure in ways that actually improve even the supervised learning case. So this is a pretty interesting technical tool, and our first papers did not use it. They used what was that guy called? What did he call it? Brutal forces? Yeah, brutal forces. This Wisconsin student used to say it was a brutal forces proof. Yeah, so the first ones are horribly nasty. I wouldn't read them. Anyway.
How do you know there's no other latent variable hiding out there? That would actually be
Awesome. Yeah, so in these settings, you're assuming that there is just the latent variable, that's the Y, and that everything's bounded in the label. As soon as you go to things that look like multitask, this assumption becomes very dubious. And so you have to be able to estimate how far away you are or how robust you are, and that's where the learn the structure kind of stuff happens. Operationally, the key question is do these estimates improve over what you had there before? And they do. And there's a bunch of work that you can do to say, like, can you estimate things that look more like those kind of semi-causal estimates to say, oh, there's not a confounder that's out there. And that's how we got into this dark, winding road of looking at causality stuff. But you're right that there's no way to rule it out. That's, you have to make some assumption here. You have to make some assumption that, like, how robust are you to model misspecification for this thing, right? If there is a z that touches everything, you're screwed. And that can happen, right? We have examples, actually, where that happens. OK, cool. The other thing I want to highlight is what this theorem actually says. And I'll just say it informally. So the thing that you can make an assumption, this gets to Ben's core point, is as long as you have enough kind of independence in the training set that's coming in, you have enough of these unlabeled points, then basically what you're able to show is that you can both recover those parameters, and in fact, those accuracy estimates you produce are valid in some sense. And they're valid in the sense that the test error decreases in the way that you would expect for a traditional supervised learning problem. Okay, this is the rate that you would expect. So it means that this weak data is just as good in some sense as the classical supervised data. The problem is that the assumption you traditionally make in sort of the supervised case is that you're randomly sampling from the domain. And when you're randomly sampling from the domain, implicitly that gives you a notion of coverage. How many of the points have you actually seen? Here, it's super dubious that you would get that coverage because you're writing functions that are kind of cranking out a bunch of stuff. Okay? So you may not cover all of the interesting cases in your label space. So you could either sample a couple hundred points and check if that happens, which is operationally what people do. But I want to highlight the generalization style bounds that we give really depend intimately on coverage in a way that you didn't have to worry about in a standard supervised case. And this is a clear weakness of this kind of theory, and it's something that we're working to address. So you do have people who basically produce these systems, and then that step about validation that I mentioned, please God don't get rid of it, because you're kind of looking for the unknown unknowns, if you like. You have to sample to find them with some kind of confidence. And we don't know how to get around that yet, but it's kind of cool. OK. So some NLP experiments. They make the assumption that you're randomly sampling from the space, so the mass on them is less than epsilon 1 over square root n applies to the entire set omega, whereas here we have like some omega 0 that we're actually targeting. So it does happen in standard supervised. You have to assume that you draw randomly from the entire population. It still happens there. This No, so the thing here is that, if you picture two circles, you have, your big set of training set. If you can randomly generate things from there, then you're in the supervised learning regime. And traditionally, supervised learning in that setting would say, if you can't sample, then you're not in our setting, and we don't tell you what's going to happen. You don't have an IID sampler.
It's not about the sampling rate, it's about just coverage.
Just about coverage. It's just about coverage. And so in this case, I say the coverage assumption to me seems more dubious than in the first one. That's an aesthetic choice. So when people look at the generalization, like, I want to make super clear what the generalization is saying. It's like within the smaller set, you're getting the same statistical accuracy that you got before. What is not guarding against is coverage. And maybe this is like years of throwing this over the wall and watching engineering teams go like, hey, we're shipping something with totally 100% weak supervised data. And I'm like, did anyone look at the output? And they're like, why would we do that? You have a theorem. I'm like, oh, good God. So this is basically saying this is a particular failure mode that seems to be exacerbated in this setting that doesn't happen as much if you do a traditional supervised setting. Go ahead. Sure.
So are you saying that the occurrence in practice of people who run the weak supervisors and not cover the classes
is larger
than people just getting samples of training?
Yeah. So you've seen it.
All those functions vote yes.
That is a danger. So anytime, and one of the points that I'll bring up later is anytime you introduce a layer of abstraction that hides something that people were going to do in models, hides writing mechanistic features, or here about actually sampling the data, you make it so much faster. People don't check for kind of sensible errors. And this is one of those sensible errors that was like really easy to catch in the old regime that seems to be trickier to catch here. So I want to highlight it. There's some combination of like theory and interfaces that could potentially get around it.
Cool. The thing that's so weird to me, like making it really fun here is like the sampling procedure for the input data is the same. It's the projection into the new feature space that's not covered. So
Right.
So what does that tell us? It's not.
So one thing I didn't, maybe is not obvious here, is that these functions can abstain. So the cases that you'll see where this happens is I write a labeling function that says when X happens, I'm super confident in it, and I'll fire a rule. When Y happens, I'm super confident. But for all these corner cases, yeah, just say I don't know. So I don't know is in there. And traditionally what would happen if you did that in like a production labeling pipeline is that would get, the L1 labeler would give it to the L2 labeler, the L2 labeler would give it to the person in charge, and they would say, oh my gosh, our specification is wrong, let's figure out what we do in this case. That doesn't happen here because you made it so fast to iterate. It's almost like a human problem versus a statistical problem. That makes sense. Super cool. Yeah, but that you got the point exactly. Okay, let's go back to radiology just for 1 second. Exact same model setup that we had there. This thing is servable on the image. This top thing is non-servable, so we're in the exact same setting I told you about. This is an AUC curve, whatever you think of it, for people labeling data. That's person months of data that they labeled. That's after person years. We got a pretty good gap. Jared went over there for an afternoon, basically, sat with the folks in ties, and wrote 20 simple rules. This is his result. He's about 1 AUC point lower. Getting back to our earlier discussion, we did an analysis of what were the different kinds of errors. The errors weren't that dramatically different, actually. There wasn't the concern that I just raised. Didn't really come up in any kind of material way. And actually, as a result of this, they started using it in a bunch of downstream tasks, which is pretty cool. So it's exciting. And the difference of like 8 hours to get started versus years to be able to correct your schema seems to be a big deal. Please, sure.
Question. So you have these nice examples here where there's negation and then how fancy do you have to be in your dumb NLP to get this stuff to work?
Yeah, so of course, the more sophisticated you are, the better. One of the things that we've seen over time as these things get used in production systems is that people kind of develop these folksonomies for like different styles of rules that work well. They have different pattern generation engines. They have like different pieces that are on top, and they generate some of these more reliably than others, which gets back to my earlier concern. So these will work well. The straightforward answer is these will work well even with relatively stupid NLP underneath the covers. People eventually get more and more complexity there, and what gets complex is a function of the tooling, not the framework. So so this is the thing that's a little bit strange. Here, I mean, it was pretty dumb. I mean, like it was what you could write in an afternoon starting from scratch. It's not like he came in with some massive library to do this. They're like, plural fusion, abnormal. Like we were intentionally trying to say like, what could you do? And I should also say, radiologists themselves write these rules now. Like we don't have anything to do with it, which is also terrifying in a totally different way. Okay, due to time, what time did I go to, 12? Okay, so I'm gonna skip the, yeah, so we'll have some questions and stuff. Okay, well, whatever. Okay, so I'll flash a bunch of slides and then I'm gonna rant for 5 minutes and then hopefully someone asks me the question so I can rant some more. Okay, so the thing I'll say here is a bunch of Nature papers about using this on video. Video is an ideal situation, so this is to use this kind of stuff. The cardiologists in this case were looking for these rare abnormalities. We don't know how often they happen, but it's no more than 2% of the general population. We went through the UK Biobank and basically had videos of their heart pumping, okay, MRIs, and we tried to look for this malformation because it has a whole host of downstream effects, and they were also doing some genetics paper which just came out. The point is doing this traditional weak supervision or this what we call multi-resolution weak supervision, which I just skipped, is dramatically more effective than the years they spent doing this hand baseline labeling. And we went back and actually did this with the cardiologists who were there. So people often ask, like, hey, how does this work beyond text? And the way it works beyond text is that you usually have some primitives that get you into an image, and then you can model like correlations across the images in nice ways. And so these are all tutorials that you can go through on snorkel.org. Intel did something on self-driving cars with it, which was pretty nice. Yep, and skip all this. Structured data, pretty cool. Visual knowledge graphs, face stuff, awesome. All right, so the two things I want to say, I want to talk a little bit about production systems. This whole thing that we've been talking about is that manual labels are like this 0-1s of machine learning. And there's an analogy that's like, sounds a little bit like two sophomores in their dorm room, but is also, I think, kind of helpful. So you can think about this in the same way we think about traditional code. The weak supervision stuff that I talked about there was like labels from code. You wrote a function, it produced a bunch of labels. And the interesting thing, though, is that now we have this piece of code, we can apply like the rest of like software engineering and like goodness to that stack and start to build more complex things. So we can start to build things that are like out of high-level languages. So we probably have 3 or 4 papers now about if you have higher-level primitives, how do you actually kind of have the analogy of libraries for these things and what problems arise? The one-sentence version is they're way more highly correlated than the traditional weak supervision setting, and you have to take care of this through a combination of statistical tools and program analysis tools. And so that's a line of work. The more sci-fi stuff we're doing is like we have these papers in ACL about supervising just from natural language sentences. So there was this one neuroscience group They didn't know how to write Python. They wrote sentences describing their images. And we basically took them and, with Percy, put it through a semantic parser and generated tons and tons of noisy labeling functions. And we showed that they could actually train models by just giving explanations. It kind of worked. Kind of cool. I have a student who just won this fellowship. His entire task is like, we strapped the people in ties, we put eye trackers on them. Where do they look? What do they click on? You know, all the exhaust that they generate when they look at a patient, can we learn from that more observational data? And can we do statistics about what is going on underneath the covers? Okay? So that's the trajectory we're on. I'll spend just a couple of minutes on this. I was just really proud of this thing unreasonably. So, you know, we got a company that was acquired by Apple. We were excited about it. They let me, one of the things that I loved about the acquisition, which was part of it, was they let me sit on my couch and write code. And as a professor, like, this is a rare luxury. You know, for some reason, you don't get to write that much code as a professor. So I was like, part of my deal, like, I want to write code. So I wrote code. Now I'm going to torture you with it. So this is a system called Overton. We just released a couple weeks ago publicly. It's been running in production for over a year. So let me explain to you kind of the principles and the rants that are underneath the covers. So it's looking at problems that are machine learning problems. And my point here is that they tend to be even simple things like how tall is the President of the United States, actually fairly complex if you're building at large scale. You have to do all kinds of things like finding named entities, finding the intent, inferring it's Trump, not the office, and firing off queries. In a real pipeline, over time, you have entire teams that are specialized around doing each one of these different pieces. And so we noticed 3 challenges. The first challenge is these things have really complicated pipelines, and often the errors are not within a piece of pipeline, but they're falling through the seams. They're the handoff, if you like, the assumptions. And then the teams fight with each other, and that's not cool. They also require fine-grained monitoring. So one thing we've been building for the last couple of years are abstractions that allow you to monitor machine learning systems really, really well and figure out where it's going wrong so you can identify these kinds of problems. Hence my whole focus on like these extra sampling techniques and software tools that allow you to go back and do it. The last thing, then, probably the thing that was most controversial when we started, was that every root cause analysis that I saw in my little slice of the world, and it's definitely myopic, the fix was to update the supervision, to clean it up, to bring in a new source of supervision. It was never to change the model. But the action was always to change the model, to write more TensorFlow code and write more PyTorch code, and this seemed crazy to me. And so this is why we build Overton. So a couple of explicit non-jobs. Engineers should not set hyperparameters. It's a waste of time. It comes with every toolkit I'm aware of. Another one that's I like to get, I gave this part of this talk at Google on Wednesday, one of their keynotes. And the other thing that's not a challenge is model architecture search in a lot of production models. You don't need to search all of the and not gates to construct, you know, the latest and greatest image model. You just need to like search a couple of hyperparameters, do a very coarse-grained hyperparameter search. And indeed, most of the production models are not the fancy neural architecture search. They're this kind of coarse-grained model search. It occupies a real important piece of what's going on and sort of underserved in the research literature. And I won't go into too much detail about this piece. So this is what Overton did. Zero-code deep learning, so it's totally declarative. If you're a database person, it looks like you're writing a schema, and it's in fact called a schema. You say all the tasks that you want to accomplish. You say all the input formats that you want, and it's up to the system, basically, except for some very crude data flow, to wire that graph up for you, pick all the models, pick everything that's underneath the covers. It was designed so that engineers did not write PyTorch and TensorFlow code. And it shifted the team. The people who used to write that went up the stack and started writing other tools, and I think being hopefully more productive. It has some improvements for monitoring and supervision. There's this thing called slicing that's in NeurIPS this year that was also developed in this. And it wraps up everything from updating supervision all the way to model deployment. Okay, so super happy about this thing. It improved production systems. I can't say what these systems are, pretty dramatically. Those are pretty big error rate reductions. And it's in a lot of places, which was really cool for us that we were excited about. But this is a column that I think is most shocking, why I really wanted to talk about it. I think there's a view in research that's different than in product. When I was at Google, multiple people came up to me and said, on Wednesday, said, hey, we don't ship a project that doesn't have majority weak supervision now. These are the numbers for production systems of how much is weakly supervised in the way that I described. It's so much cheaper to generate that once you get access to the kind of tools like this, like it's the first thing you start with, not the second one. And that was really exciting to watch that switch. It's used by a bunch of folks. It's been really cool. Okay? There's tons of related work. Please check our blog where we tell you about all the things that are related to weak supervision. To keep the story compact, I didn't, but it's related to tons and tons of stuff, and we try to keep that up to date. And there are a couple of courses that are now about weak supervision that I'm happy to point you to. All right, so to conclude, we talked about Snorkel. I gave you this nugget of statistical estimation and structural learning. And this last bit is the one that I'm kind of most obsessed with right now is it changed how people program. Like they didn't spend time writing TensorFlow and PyTorch code. They spent it kind of dealing with supervision, building models on top of that, and they were potentially more productive. And I think this idea of how machine learning is changing in production systems is super interesting. Karpathy wrote this blog post that I really love, that some other people didn't like as much, which was about the software 2.0 stuff. And the thing that was interesting to me is in this and in the zero code deep learning, it was things that like we built and thought were really controversial. And then you find someone at Tesla, someone at Uber, someone at Google who are thinking along the same lines. So there's something going on here that this combination of like weak supervision and a higher level of abstraction seems to be catching on in some places. And it's super exciting to see in a bunch of different things. You can check out the snorkel.org thing if you're interested in following up. Thanks so much for your time and attention. Questions?
Very interesting talk. So I think I agree with this. Even Andre is saying that Tesla 25% is now the new model, 75%
Right.
data.
Right.
So this is very interesting. So is it possible that many of these labeling functions that you're writing, it could be that all of them agree on something that's wrong?
Yeah, awesome.
Do you reject them? Like you don't want to have some noisy data, right?
Yep.
So is there like a pipeline that you reject even if all of them?
So traditionally the way I've seen this deployed, and people deploy it in different ways, is as I mentioned, there's a separate validation step. And so what will happen is you'll run the weak supervision, and then you'll do the most important thing. I actually have an entire lecture of 229 that's basically titled, Look at Your Data. Like that's all, just repeat it 25 times. So what happens is you produce that, and then you sample some of the output of the weakly supervised things and say, are they all agreeing in crazy ways? And if they're all agreeing in crazy ways, it's like any other debugging task. Why are they agreeing? Are they agreeing because their code is wrong, because there's some assumption we were making that was wrong? That debugging task I've been interested in and we've written some things about, but I don't think we have any kind of systematic solution for it. But yes, the short answer is it can and does happen. And that's why having it in this larger pipeline that like monitors for you is super important. Please.
Try to understand how the programmatic labeling might differ from other forms of supervision,
Mhm.
say, mechanical terms. So
Mhm.
understand it can be
Sure.
much cheaper.
Sure. Sure.
And then integrate with the software.
Yep. Awesome. That's absolutely wonderful. So one thing about Mechanical Turk in general, or like the lower tier labelers that folks have in organizations, they're not actually for subtle judgments. They don't actually agree that much. And so even if you give them a fairly concrete spec, they may disagree about the cases. You may want it way one, but the new labeler comes in who's only 2 days on the job or just doing a micro task and says, oh, that doesn't make sense to me. I'll put it in this other bucket. So one of the other things that people like about it, in addition to the things I mentioned, was that it somehow is more systematic in the errors that it's going to make. And that sounds really bad, like making systematic errors, but it's actually really good because it means that you can start to correct them. So the fact that you can rerun all of the supervision whenever you want, that interaction mode is kind of radically different, so you can tweak it. It's also potentially bad in the ways that we've discussed, right? Like you may have a small coverage, you may delude yourself in some ways, and dealing with any large code base is not like ostensibly all that much better than dealing with a bunch of huge humans, right? There are other kinds of failure modes that you're introducing. But that difference in the abstractions, I think, allows it to be successful in different places. If you have access to large, high-quality hand labelers and they cost $0, like you should use them. There's no reason not to get perfect labels. It's some kind of engineering trade-off of like how easy is this thing to write, how precise is it to write, and those are kind of the dimensions to evaluate it on. Like how systematic is it, what's its quality, and how quickly is it to fix when you've screwed up. I think the thing we underprice in research is like we build the data set and we think we're done. And that's never been the case. Like there are teams, their whole job is just to maintain training sets for machine learning models. That's all they do for 2 to 3 years until the product, they move on to a new product. And I'm just saying like, hey, there's some software tools we can put in there. These may not be the right ones. They almost certainly are not. But people are using them even though they're so crappy. Please. Sure. Exactly right. So you're exactly right that we're trying to get rid of the training part of the pipeline where you have to kind of fill out the structure and you need millions of points. Validation for accuracy, you tend to need orders of magnitude less data. So that's why it's an engineering win. But you're right, we've pushed the problem now into validation. Some of the crazier ideas we're thinking about now, I've learned as I've been a professor longer, that when students come into your office and say something that sounds like heresy, I used to be like, God, that's a terrible idea. Now I'm like, that's probably a really good idea and I'm being stupid. So one of those ideas that terrified me when I first heard it was someone saying like, well, actually, your test sets, I know they make you feel very comfortable, but that's not how I evaluate how well I'm doing. I look at my output and I kind of browse through the results and kind of do this little process on them, and that convinces me more than any test set. And I record what I've looked at. And I thought it was pretty interesting because that's where this exhaust idea came up. Maybe there are ways that we can further relax that validation. And then we started this whole line of trying to prove situations, which come up in standard transfer learning, when you're saying, hey, did I cover enough of the space? Like, we take that for granted in transfer learning a lot of the time, but it's not clear at all. And are there tools that allow us to measure that? And in medical applications, that's really critical that it's going on. So you're right, we've just in this work moved the pipeline there, and hopefully there are some things that we can do to even reduce it further. But you got it exactly right. Oh, please.
What if I wanted to write a rule that was not like 1 or 0 or 1 or something? Like, what if I
Awesome.
wanted to write a rule that was, well, in this case, I'll just say it's 50-50, or it could be this.
Awesome. Yeah, so there are situations where people want to express priors, and especially in places that are extremely, I would say, sparse, like the label set is really large. Let's say you wanted to give feedback. This is one that actually does kind of happen. You have a huge set of labels, and it's not labels, 100 to 10,000, but you're not sure which of these 3 it is, and you'd like to express that uncertainty. That multi-granularity stuff that I was talking about, that's the kind of direction that it goes into. Now, the thing that I'm dogmatically believe, which is probably false, is that people can't reliably give you numbers of how accurate they feel about these things. And so trying to relax that interface is super interesting. But the way we've dealt with that in the applications we've built is to say, okay, you can give this kind of supervision that says, I don't know it's in any of these classes, but I'm not sure which ones it's in. It's possibly in this set of 3, but I'm not sure which one. And you can give me some ref scores that we're free to kind of munge and supervise around. But that last bit of scores, I'm very, very skeptical of. People do give us that information, and we do use it, but it seems like it's opening a whack-a-mole situation. But you're exactly right. Sometimes you can't get supervision that's so precise, and that's a super exciting challenge for us. Very, very good point. Cool. Right. Awesome. Awesome point. So yeah, so there's 2 things. So first, that's an extremely optimistic view of humans, and I love it. So no, being serious, it's true that a lot of these things, the kind of disagreements among labelers are ultimately fixed by a human process. Like when you build these kind of applications, one of the most important persons is the PMs, who actually sit above the different labelers that are triaging and say, you folks have seen these examples, you've looked at hundreds, and you disagree systematically, come together and talk. And that monitoring stuff that we built into Overton was to try and identify, there's a whole bit about computing confusion matrices that's about identifying exactly where are you disagreeing systematically with someone else. If you can fix it through a human process, absolutely 100% do so. The game here is a little bit different. We are, assuming that we don't have the ability to fix and rectify that information. There's another thing which I think was buried in your comment that I really like too, which is, isn't there information that they can exchange that would somehow tell us more about when and where they disagree? So it's not just kind of coarse-grained like, oh, you're highly accurate and you have different expertise or something like this. And we've done a little bit of work on that where you try to learn the conditions under which you should trust labeler 1 versus labeler 2, and in a way that someone could look at the output and say like, hey, you trusting this extractor, but we've done stuff that's really boring. It's nothing as exciting as you're proposing. It's like, oh, this extractor works really well on HTML, but it doesn't work on Word docs. And so we kind of surface kind of topic clusters for people to look at and say like, it's working really well over here, but not over here, and then use that side information to better estimate the accuracy. So all of these things are open on how to do. The other bit is, in the process of 2 people communicating, they put a lot of information, in chat or Slack or however they're talking. That all seems like exhaust that would be really interesting to figure out, like, can we automatically suggest how to encode that? Because the problem is the people having that conversation often are not the one that are writing the specification. They're not able to write it precisely in Python, and they may feel, yeah, I think class A and B are the same. And the developer who's sitting, in an entirely different building is thinking, no, like if you make those the same, like the application will cease to function. We won't be able to run anymore. So those conversations are super interesting to track and potentially to kind of overrule based on who owns the application. Super exciting ideas. Awesome.
You are. I would have stopped in 10 minutes ago if I knew.
It's a shame.
People have to go to lunch, Chris. You know.
People got to eat.
Shame, I know.
You didn't even let me rant about my stuff, man. These eyes. You didn't let me talk about these eyes. No. I'll show you afterwards.
They are creepy.
Yeah, they are creepy.
Everyone wants to hang out and see the eyes. They go have to think about the eyes. One day they've done that. No. You didn't tell me then. All right, look at all these things that we're running into. Well,
Amazing.
anyway, let's all thank Chris again. You're going to the database seminar. So there we go.
Am I?
There we go.
Awesome. I have no idea where I'm going. Awesome. Look at that.
Talk about eyes.
I could talk about eyes.
If you'd like to have a room to meet with students actually for the hour, that'd be fine.
Sure. Either way.